Hello, I'm your host, Jackie Mullins, and welcome to From Cells to Us. How? The podcast where we figure out how life went from a single cell to complex creatures like us. Last episode, we watched RNA accidentally create its own boss. DNA showed up, same basic blueprint, one oxygen atom removed, and suddenly RNA had a filing cabinet that actually worked. Stable, double helix, built-in backup system. The Queen of England, just sitting there, all high and mighty, looking important, holding all the hereditary information. But RNA, it's still the British government, still doing all the work. So we've got our team assembled. DNA storing information, RNA reading it, peptides helping with chemistry, and a fatty acid membrane holding this whole circus together like a bouncer who's really bad at his job. Because things are still getting in. But it's not just the membrane who has some gaps here. It was chaos in that protocell. RNA would read DNA, grab some amino acids, stick them together, but there was no system, no organization. It's like if you walked into Subway and instead of being like turkey, lettuce, tomato on wheat, you just said meat, bread, stuff, and hoped for the best. Sometimes you'd get a sandwich. Sometimes you'd get a pile of ingredients thrown in your face because that Subway worker is like, yeah, screw you, buddy. Life needed a menu, a way to say this sequence means this amino acid every time. Not, hey, give me stuff. Life needed a language. Today we're talking about the genetic code, the 3-letter words that tell RNA exactly which amino acid to grab next, that tells the umbrella people which potato head to grab. And this code is so universal, so locked in, that bacteria to blue whales to you are all speaking the exact same molecular language. Let's get into it. Okay, so let's picture our protocell situation here. DNA has sequences, long strings of A, T, G, C. That's the information. Great. RNA reads those sequences, and then what? How does RNA carry out what DNA is saying to do? Because we figured out how to keep instructions, right? We transferred information from tissue paper RNA to a fireproof safe of DNA. But how do those instructions get carried out? DNA cannot perform its own chemistry like RNA, so what's next? Well, in the early days, like we just talked about in episode 3, RNA would fold up, maybe grab an amino acid that happened to fit in one of its pockets, stick it to another amino acid, and boom, a peptide. But which amino acid? Oh, whichever was nearby, whichever fit. It was like grabbing 3 Scrabble tiles out of a bag blindfolded and hoping you spelled something. Maybe you'd get cat, but most of the time you'd get zigum or something like that. And look, this worked okay for a while. Random peptides would form. Some would be useful. Most would be garbage. Natural selection would sort it out. Classic evolution, throw stuff at the wall and see what sticks. But here's the problem. You can't build anything complex with randomness. You just can't. Life needed precision. Life needed to go from cavemen, grunting and pointing, to Babylonians in the first civilization that could read and write. That's a big jump. And this big jump started with what else but RNA. The champion of change, the versatile veteran, the Colossus of Catalyst, the Colossus of Catalyst. Shut up, Tommy. It's your very own RNA. So RNA confused me in college. I was like, why? Why are there so many? Why don't we name them something else? Everyone knows if you don't capitalize the first letter in front of those 3 capital letters, we're just going to ignore it. Like, are we talking about RNA, rRNA, tRNA, mRNA? They all look the same when you're speed reading through a textbook at 2 a.m. Also, because they sound so similar, I'm personifying them here. You don't want to hear me say tRNA, rRNA, mRNA over and over. That's boring and that's lame. And I'm not like a regular mom. I'm a cool mom. So we're giving these 3 RNAs names. Pay attention, because this is going to be throughout. It's way easier for you and me. tRNA, transfer RNA, is going to be Tina. rRNA, ribosomal RNA, is going to be Rick. and mRNA, messenger RNA, is going to be Mary. So I have all the RNAs down pat now, and I have to say I'm very glad that I do, because I am truly RNA's biggest fan. It's literally the genie from Aladdin. The cell is like, hey, we need you to do chemistry. We need you to give up storing information and make another molecule that can do it better. But also we need you to be the runner between DNA and proteins. And RNA is all like, poof, what do you need? Poof, what do you need? Poof, what do you need? But this poor sucker is never being freed. And I just want to let you know, I'm going to make an RNA fan out of you too. Listen, Al, make a fan out of you. We are heavy on Disney's 90s right now, and I am not hating it. So for the next few minutes, I'll be discussing how these 3 RNA strands specialized, how they learned and evolved to read DNA's instructions to make proteins, how RNA became the runner between DNA and proteins, like what they're doing inside of you right now. Now, because they evolved from how they were previously, I'll have some episode 2 recall. If you don't remember, don't worry about it. I'll give a brief remember this section just to jog your memory. But again, don't stress. Remember, our main issue here is how RNA figured out how to take DNA code and make proteins that could work. And that took 3 kinds of specialization. We'll need an RNA to pick the correct amino acid every time. We'll need a place where we can attach the correct amino acids together in the correct order. And of course, we need the directions from DNA. First up is tRNA, transfer RNA, our TINA. So remember from episode 2, when I said that sometimes when RNA folded into certain shapes, it would accidentally grab an amino acid nearby. And that sometimes it wasn't completely random. Like if there were a few amino acids milling around, one might have a higher probability of being grabbed just because of how the RNA folded. Like maybe when it folded, it had a negative charge in that pocket, and that specific amino acid had a positive charge. So that type of fold grabbed that specific amino acid more reliably. And so on and so forth, with different folds being better at grabbing specific amino acids, until natural selection kept the RNA sequence that reliably grabbed one specific amino acid every time. So basically, instead of panicked umbrella people just trying not to get wet and pairing with whoever, you remember those nucleotide hussies, well, now they had standards, a specific fold for a specific potato head. Specific is very hard to say over and over. Anyway, these umbrella people had tired of their hedonistic ways. They'd settled down, found their one true amino acid. RNA was going steady. So natural selection kept the folds that successfully grabbed useful amino acids. And over millions of years, you ended up with RNA molecules that were really good at grabbing one specific amino acid every time. Those specialized RNA molecules, tRNA. We have TINA, and TINA is called the delivery truck of the genetic code. If you need a visual on what TINA looks like, picture a claw machine. You know, the claw. The claw decides who will stay and who will go. TINA reaches in, grabs one specific amino acid, and delivers it. That's TINA's job. So, one type of RNA down, tRNA or TINA. Now 2 to go. So right now, I just wanted to say this isn't a full-fledged TINA, which we have in our cells today. This is a proto-TINA. It's kind of like an intern. So we've got our proto-TINA, the molecular delivery trucks. TINA grabs a specific amino acid and brings them, well, shoot. Where are they bringing these specific amino acids? It took so much effort and selecting for, but now you have nowhere to go. You can't just have trucks driving around aimlessly. We need a factory, a workstation, an assembly line. Enter rRNA, ribosomal RNA, our second type. Here's Rick. Now, ribozymes. Let's do a quick flashback here. These are those folded RNA molecules that could act as enzymes, making reactions happen faster. Remember, not waiting for magnets to snap together on a table, but pushing them together? Well, some ribozymes got really good at one specific job, linking amino acids together, or making the potato heads hold hands. And these RICs weren't only grabbing random amino acids anymore, they were positioning them perfectly, holding them steady, snapping them together into chains. Peptide bond after peptide bond. It's like forming a friendship bracelet where you have to glue each bead to the next one. And Rick was doing all of this. And these RICs, well, they started getting kind of cliquey. They were clustering together. A bunch of cool guy RICs just hanging out, all really good at making potato heads hold hands. And word got around. This became the spot to be, the hot spot, where Tina trucks could drop off their single, unattached amino acids to be linked up with a lovely new chain of friends. Rick was basically a matchmaker for lonely potato heads. But remember, RNA is still fragile. That hasn't changed. What has changed is, remember when a ribozyme would just keep linking amino acids? Just keep having potato heads grab hands, and the chain got so long it popped out of the nook RNA provided? And instead of just waving in the wind, these long peptides wanted to be useful. They wrapped themselves around the other parts of the RNA strand, like wrapping a sprained ankle, keeping it steady, keeping it from falling apart like the other RNA strands. Well, Rick liked that, and so did natural selection, so they kept it. And here's the part that blows my mind. This accidental extra long peptide chain that just happened to wrap around the RNA, well, now it's essential. It's like if you were building something with wood and you were pushing the pieces together, but they're not really meant to stay like that. So you drill a bunch of nails in and it holds, hopefully for a while because you need that shape for your end product. These peptides formed around Rick, locking him into the correct shape. And we know how important the right fold is, right? Fold defines function. If a piece of paper folds into a cup, its function is to hold water. Well, these peptides were locking Rick into one job, linking amino acids together, pigeonholing him. And what an important job to be pigeonholed in. Tina needed somewhere to bring her amino acids, and now Rick was that place. A rigid structure held in shape by peptides, but still keeping that special fold that could catalyze reactions. Still able to snap those amino acids together into chains without fear of, dissolving into a puddle. And this new combo, proteins plus ribozyme, it has a special name, the ribosome. Not the ribozyme, the ribosome. I know. Well, proto-ribosome at this point. The ribosomes in your cells today, yes, we literally have these in our cells right now. They're more complex, but they still have the same ancient RNA at the core. Billions of years later, still doing the same job, which is pretty cool. And you can kind of think of the ribosome as like Darth Vader. He has these awesome powers he can use, but he's fragile, broken, wouldn't survive long without help. Then wrap him up in that life support armor in obsidian black, obviously, and suddenly he's running the Death Star. Well, that's Rick. The rRNA inside is fragile. It would fall apart on its own, but wrap it in proteins, and now it's stable, now it's powerful, now it's a ribosome. So to be clear, a ribosome is rRNA and proteins. So the ribosome is just ribozyme 2.0. A catalytic RNA just got an upgrade to a ribosome. Same RNA core, now just with protein support, making it the go-to spot for all the single amino acids that just want to mingle, that just want someone to bond with. So let's think about how far we've come. We went from a scramble of clueless RNA strands randomly grabbing amino acids out of the molecular junk drawer, thanks leaky membranes, to mashing them together if they happen to be close enough, to now, 2 specialized RNAs with 2 specialized jobs. Tina grabs a specific amino acid and brings it to the party. Rick is the party, linking those amino acids into chains. Peptide bond after peptide bond, eventually proteins. As a reminder, I know I'm interchanging peptides and proteins. Here's the deal with that. A short chain of amino acids is a peptide. A longer chain that folds into a functional shape, that's a protein. So it's about length and whether it's doing a job. For now, just know they're both chains of amino acids. Peptides are the baby version. Proteins are all grown up. So right now we have tRNA, Tina, carrying specific amino acids, and an upgraded ribosome, complete with rRNA, Rick, and proteins, linking amino acids together. 2 down, 1 to go. We have our last RNA type, mRNA, messenger, our Mary. So here's where it gets a little tricky, because in early protocells, there wasn't really a separate Mary yet. I had a hard time deciding when to introduce you to Mary, and ultimately decided now, earlier, even though Rick and Tina weren't really friends with Mary yet. Because Mary's job was to take the information DNA had and bring it to the party, bring it to Rick. But at this time, at this proto-time, that wasn't really happening. So if I had to make an analogy of these 3 RNAs, I'd say Tina was the DD, the designated driver. She made sure she picked up the right people, the right drunk amino acids. Rick is the owner of the party, just waving people in. He trusts Tina, the DD, to have brought the right people. But Mary has the party list, the special order the guests need to arrive in. However, Rick at this point, he's a freshman, a noob, an overconfident fool. He ignores Mary and just starts attaching the amino acids Tina drops off in whatever order. The drunk amino acids form a conga line and, parade themselves through the house, out the back door, holding shoulders in a firm peptide bond to be free onto the world. Now Rick doesn't listen to Mary, so that conga line of amino acids may or may not be useful. So why do we need Mary? Well, DNA has the instructions. Great. But DNA doesn't move. It's like all those happy couples of AT and GC have paired up, and now they don't want to go out anymore. They're going to stay right where they are, cuddled up on the couch watching reruns in the middle of the cell. They're happy. They're not going anywhere. So how does Mary get this information from DNA? Does it beat it out of them? Let out some pent-up frustration at having their job taken? Listen, I'm going to give you to the count of 10 to get you ugly, yella, no good keister off my property. I mean, a little bit, but physics is doing the beating up. Just like last episode, physics shakes the DNA double helix open, so it's got 2 open strands, basically 2 magnetic strips, just waiting for the opposite piece to click into place. Free RNA nucleotides come in, AUCG, to make a small copy of the DNA strand. When the copy is completed, now we have our Mary. So Mary isn't floating around pre-made, just waiting for its chance. Mary is a copy of DNA's instruction. It can't be a strand until it has an order, and it doesn't have an order until it's built off of DNA's template. Just like how individual Lego bricks aren't really anything great until you read the instructions on how to make Ron Weasley's flying Ford Anglia, which my son just got for Christmas, and I am really excited to build with him. Now, you also might be a little confused. Yes, you think to yourself, we did just talk about this last episode, and that was about DNA copying itself, not Mary. What's the difference? Well, the difference is if it's DNA nucleotides forming on the unzipped DNA or RNA nucleotides forming on the unzipped DNA. It's like an empty parking lot. Same spaces either way. But if a fleet of cars show up, you get a lot full of cars. And if a fleet of trucks show up, you get a lot full of trucks. DNA nucleotides show up, DNA strand. RNA nucleotides show up, you get a Mary. We're unsure how early protocells signaled whether it was to make a DNA strand or an mRNA strand, a Mary. Today, there are precise instructions, but back then, maybe it had to do with how far the DNA unzipped or what type of physics caused it to unzip, or maybe it was just a free-for-all. Whoever got there first, like that cheese wheel race downhill. Things are just flying around. No one really knows what's going on, but they're all moving. Also, I know I haven't really mentioned the different nucleotides for DNA and RNA. It is important, but we'll tackle it for next episode. For now, just know that RNA uses a U, where DNA uses a T. All right, that is a lot of information. Let's do a checkpoint. Let's go through the RNA family. We have tRNA, which is our TINA, and it carries one specific amino acid. It's the delivery truck, the DD driver to the party. Then we have rRNA, our RIC. It does the chemistry, makes peptide bonds between the amino acids that Tina brings over. He's inside the party house, making the correct guests hold each other's hands. mRNA, our Mary. Mary carries the genetic message that was copied from the big dog himself, DNA. Now, Mary wants to be included in the party. It knows it has important information but is being ignored. Also, I'm doing more personification here. Mary never actually shows up at Rick's party. More than likely, Mary is just drifting around the protocell with this wealth of information not being fully utilized yet. So all three are RNA. All three descended from those original RNA molecules, the ones that did everything, that could grab things, catalyze reactions, store information. They just each picked a specialty. And all three are about to come together and do something incredible. So that was fun. Are you a fan of RNA now, or are you too annoyed at how many there are? Either way, you can't deny they are impressive. So we have the players, but how does the code work? You understand that DNA gets shaken open, then by luck, speed, or physics, free RNA nucleotides attach themselves to the open DNA strand, forming a Mary strand. Mary has DNA's information, but Rick has not seen it. Tina is picking up specific amino acids and bringing them to Rick. Rick is combining them into a peptide all willy-nilly. Meanwhile, Mary turns away dramatically as its special list is dropped, wafting in the wind, and somehow lands in a puddle. And the conga line full of amino acids form a maybe useful, maybe not peptide chain or protein. So at this point in the protocell life, things are getting more organized, but we're not quite there, as you see. Step by step, we get closer. Now we are grabbing the same amino acid every time, but we're not doing it in the right order. Now we have a specialized RNA that binds amino acids together, even if the nooks aren't right next to each other. But he has no clue what he's making. We need to get Mary involved. How does that happen? Well, I won't lie to you, fine folks. We simply don't really know. This is one of the big mysteries on how life began. We know what the system looks like now, but the exact steps of how Mary went from ignored list in a puddle to instructions everyone follows, well, that's still fuzzy. Here's what we do know. Somehow, a connection formed between Mary and Rick, meaning Rick started listening to Mary and then started bringing over Tina's in the right order. And that connection came down to 3 little letters, to the universal code, to the language every cell alive speaks today. So we know it happened eventually, though unsure how, but right now we're at the part where Mary is getting noticed. And not only noticed, it's the big man on campus. It's like when Tyler Posey went from second string lacrosse player to absolute starting stud, thanks to those sweet werewolf genes. But Mary doesn't have werewolf genes. It has a special sequence of letters, which I would argue is better, as there are no worries about the full moon. See, these very special letters, well, they dictate which amino acid Tina needs to bring over. Some of you might be ahead of me here. Like, hey, how can 4 letters dictate which of the 20 amino acids to bring over? How do you map RNA letters to amino acids? Early life tried a bunch of options, per the usual, but here's what it settled on. 3 letters is equal to 1 amino acid. Those 3-letter chunks are called codons. Say it with me, codons. That's from Brother Bear. I'm not being condescending, although I think Coda was. So you might be thinking, why 3 letters? Why not 2? Why not 4? That's a great question. Let's do some math. I know, it'll be quick. So what if we just had 2-letter codons? RNA has 4 bases. If codons were 2 letters long, 4 times 4, 16 possible codons. Life uses 20. 2 codons wouldn't be enough. Well, how about 4 letters long? That would equal 256 possible codons. That's way more than you need. That's wasteful. That's like 10 buns and 8 hot dogs. You should probably remove the superfluous buns. But if codons are 3 letters long, 4 times 4 times 4, that is 64 possible codons. That's perfect. That's enough to cover all 20 amino acids, with some extras left over for redundancy, which actually helps. We'll get into that in episode 5. 3 letters is the Goldilocks zone. Not too few, not too many, just right. And that's what life picked. 3-letter words, the genetic code. So let's do an example. Let's do code AUG. That is a codon that means grab methionine. When Mary shows up at the party with its list, Rick reads it and calls for Tina, the DD, to bring methionine to the party. Now, each of the 20 amino acids has a specific 3-letter codon. But because there are 64 options, some have more than just that one. For example, if Mary brings over GGU, or GGC, or GGA, or GGG, Rick will read it and ask Tina to bring glycine. Glycine has 4 codons, 4 words that mean glycine. But there's only one for methionine, AUG, and that's important because that's our start here codon. When Rick sees AUG, it knows this is where we begin building an important peptide chain, one that will eventually fold into a working protein. It's like the capital letter at the beginning of a sentence. So Rick reads the code AUG. It calls for and grabs the start amino from Tina. Then it'll read the next 3-letter code from Mary's list and keep calling Tina over with the corresponding amino acid. The amino acids keep coming, and Rick bonds them together, now sending out a protein with a much higher probability of working. This is now Ford's assembly line miniaturized, microscopically miniaturized. So does this chain just keep forming? More and more amino acids get attached to the chain until the cell explodes? Much like when I never say when the waiter starts grating Parmesan cheese onto my pasta, the whole restaurant explodes. There are no survivors. No, kidding. Obviously, the peptide doesn't just keep getting built on one strand. That'd be crazy. You wouldn't be able to do anything with it. Rick stops calling Tina over when it hits the stop codon, UAA, or 2 others. When that comes up on Mary's list, that's when they tie up the knot and send that peptide on its way. And also, the waiter always just stops on their own, which is kind of annoying. Like, why even tell me to say anything? Maybe I should start speaking in codon. Just yell UAA when I want something to stop. Or I should tell my kids to start talking to each other that way. Well, Jane, Joe did say UAA, and that is the universal code. Maybe you should listen to it too. Oh, don't you AUG with me, young lady. All right, so there you have it. That's the universal code. And it's not like a start codon is different for you or me or E. coli or that mold that was growing on the water cup in the beer pong in that gross garage. How we all survived, I don't know. The start codon and all codons are the same for every living thing. And I want that to really sink in, because what an amazing thing that is. Take a cell from your body, a cell off a slug or an oak tree, and inside the instructions are the exact same. The cell is starting peptide chains at AUG and stopping at UAA. And because all living things have it, that means it evolved once. Somewhere around 3.5 to 4 billion years ago, this system locked in, and everything alive today inherited it and kept it. So let's do a quick recap, because that's a lot of good information there. So what was the problem? RNA was still kind of winging it. They were grabbing specific amino acids, but putting them together in a random way, making unknown peptides. Sometimes useful, sometimes garbage. You can't build anything complex like that. The solution: 3-letter words made of nucleotides, AUGC, that each specify one amino acid. 4 times 4 times 4, 64 combinations. That's plenty for our 20 amino acids. AUG, our start here, and grab methionine, the capital letter at the beginning of a sentence. UAA and 2 others is stop. Tie it off, send that peptide on its way. The code is universal. You, me, E. coli, slugs, oak trees, beer pong mold, all using the same dictionary, the same start, the same stop, the same everything. That means it evolved once, about 3.5 to 4 billion years ago, and nearly every living thing inherited it. We went from blindly grabbing Scrabble tiles out of a bag to a 64-word glossary that tells you exactly what to do. That is not a bad transition. All right, so now let's watch this whole system in action. Here's how the letters or codons changed the process. Now imagine Rick, and he's throwing a party again. He's a senior, or you know what, better yet, he's an adult. Out of college, the kegs and solo cups are replaced by fine wine, IPAs, and glasses with charms on them. Rick is wiser, more learned. He waits for Mary to show up this time, because now order matters. He reads the guest list Mary presents, 3 letters at a time. He uses each codon to call for the right Tina. First up, AUG, the start signal. The Tinas, or DDs, show up in proper order, each dropping off their specific amino acid passenger. Rick connects each amino acid like before, but this time following Mary's list. The conga line keeps forming until Rick reaches UAA, the stop signal, and then no Tina is called. The peptide conga line is sent out the back door, this time most likely working, most likely what the sequence wanted, and for early life, that difference was everything. So, with real names this time, just for a check-in. So, rRNA is just reading the mRNA like a script, calling for the right tRNA each time, and stringing amino acids together in the exact order the mRNA specifies. That's translation, reading the genetic code and turning it into a protein. Also, probably why you realized I changed the names a little. Just that one sentence was a little brutal. Now let's be real, early translation was rough. The proto-Tinas wouldn't always show up on time. Were probably out the night before, classic Tina. Sometimes the wrong Tina would arrive. And sometimes Rick would skip a letter or read the wrong codon. The whole system was like a middle school play. Everyone's trying their best, but there are missed cues, forgotten lines, and at least one kid who is clearly winging it. Or one kid who is a playing card soldier from Alice in Wonderland and only has one line, and it's written for them on a scroll, and they open the scroll upside down and run off the stage instead of saying the line, just as a random example. But here's the thing. Early Earth's motto: it was good enough. Even with errors, the party house ribosome could churn out peptides that were mostly correct. And mostly correct was infinitely better than completely random. Natural selection took it from there. Protocells with better translation systems, fewer errors, faster assembly survived better. They outcompeted the sloppier cells. And after millions of years, the system got refined. The party house Rick was in, it got bigger, more complex, more accurate. The Tinas got better at listening to the Ricks and grabbing the right amino acid. But the core was always there. 3-letter codons, Mary to Rick, and Tina with the delivery. The code was born. So let's do a quick recap. mRNA, Mary, carries the genetic message, a sequence of codons, from DNA. tRNA, Tina, brings specific amino acids. Each Tina matches one codon. rRNA, Rick, reads Mary's list 3 letters at a time. Each codon calls for a specific TINA. Each TINA delivers a specific amino acid. The RICs link them together into a protein chain. That's the genetic code in action. DNA stores it, mRNA carries it, tRNA and rRNA translate it into a protein. That's the genetic code in action. Information becomes reality. So why does this matter? Why is the genetic code such a big deal? Well, because now for the first time, life could build the same protein over and over again. Before the code, RNA grabs random amino acids, makes random peptides, hopes for the best. Fingers crossed, After the code, DNA says, make this exact protein. Mary copies the message, Tina delivers the ingredients, Rick assembles them in the correct order. Same protein every single time. Reproducibility. And once you have reproducibility, you can build complexity. You can make proteins with hundreds of amino acids in a specific sequence. You can make enzymes that do very precise chemistry. You can make structural proteins that build cell walls, or transport proteins that move molecules around, or regulatory proteins that turn genes on or off. It's almost endless. You can build systems, networks of proteins working together. The genetic code turned life from random chaos that occasionally works into organized machinery that works reliably. It's the difference between a pile of car parts and the actual car. However, there's always a however, the code isn't optimized yet. At the time we're talking about right now, it's not standardized. Different protocells might be using slightly different versions of the code. Maybe AUG means one thing in one cell, but something else in another. It's like traveling to another country where they speak a different language. Sure, you can communicate, point at things, make gestures, hope for the best, but it's slow and sloppy. You order coffee, you get a beer, it's 10 a.m., but honestly, it'd be harder to explain the mistake than just to crack it open. As always, I'm talking about a friend. That's what early life was like. Everyone kind of speaking, but not in the same language. And the code is still sloppy. Errors are everywhere. There's no quality control. Life needs this code to become universal, locked in, the same across life. And why? Why do we need that? Well, because if every organism is speaking a slightly different molecular language, they can't share genes. They can't swap useful innovations. They can't evolve together. They're isolated. But if everyone speaks the same language, now you can trade. Now you can share. Now evolution kicks it into high gear. So how did this messy, error-prone code become the universal language of all life on Earth? Well, that's a story for episode 5. Let's zoom out and see what we've covered. It was a good one. RNA didn't just sit back when DNA took over storage. It specialized. It became 3 different types of worker. tRNA, TINA, delivery trucks carrying the amino acid. rRNA, Rick, was living inside the ribosome, linking amino acids together. mRNA, Mary, was the messenger carrying the instructions from DNA. And together, they invented a language, 3-letter words called codons, each one meaning a specific amino acid. The party house ribosome with Rick inside reads Mary's list 3 letters at a time, calls for the matching TINA, and assembles amino acids into proteins. That's translation. That's the genetic code. It was messy at first, error-prone, inconsistent, but it worked, and natural selection refined it, improved it, standardized it. But we're not done yet, because this code, this 3-letter language, is about to become universal. Now, you might be thinking, oh, wait, you already told me it was universal. And yeah, I did. Spoiler alert, I suppose. But here's the thing, I told you where it ends up, not how it got there. Right now in the proto world, different protocells might be running slightly different versions of the code. It's not locked in yet. It still has to prove itself. It still has to outcompete every other version until one wins. And one will win. One version of the code will spread to every corner of the earth. Every living thing will speak it. Every bacterium, every plant, every animal, every cell in your body. And once it's locked in, it will stay locked in for 3.5 billion years. Now that's what I call a winner. Next time on From Cells to Us, how the genetic code gets refined, life discovers error correction, the central dogma is established, and Luca. Now I know I was Disney heavy this episode, but no, not Luca, the fish boy. Luca, the last universal common ancestor, emerges, and all the pieces finally start working together. I'm excited. Also, 4 quick notes for the end here. 1, I always thought it was pigeon holding, not pigeonholing. I literally thought they just meant that pigeons had really strong grips. So if anyone else thought that, it's not. 2, I totally stole that Parmesan cheese joke from a meme, just so you all know. 3, when I say all living things had this code, it is 99.9% true. There are a few very rare deviations like mitochondria. They still had the universal code, but it deviated afterwards. I just wanted to make sure I was clear. And 4, maybe you're thinking to yourself, why am I still listening to this podcast? And if you are, I get it. These are complicated topics, but you're doing amazing. You're learning the universal language of the cell. Other people brag about speaking Mandarin or French or Spanish, but you can always hit them with, oh yeah, how about the universal language, bud? That one every living thing on earth speaks. And this stuff matters more than sounding smart at parties. You remember the mRNA vaccine for COVID? That's mRNA, the same messenger RNA we just talked about. That's our Mary. I mean, now you can pick up a scientific paper about that and understand more than you could have 4 episodes ago. Bottom line, I'm proud of you for getting this far. This is not an easy subject, and you've stuck with it for 4 episodes, so you're awesome. And thank you for joining me on this biological journey. I'm Jackie Mullins, and this has been From Cells to Us. How? See you again next time.